Welcome everyone. Today we are here to discuss a topic not unfamiliar to us final year students in electrical engineering, but with a more philosophical approach. For that question, ask yourself, what is it that amazes you so much about electrical phenomena? My colleague and I choose to focus on a fundamental aspect, electromagnetic induction. And we hope that by the end of this video, you'll see the beauty behind it. Before diving in, let's start with a short introduction.
Electromagnetic induction, or EMI, is the principle that powers our modern electrical world, from power plants right down to charging our phones wirelessly. Michael Faraday discovered electromagnetic induction in 1831. He observed that a changing magnetic field induces an electromotive force, or EMF, in a conductor. Later, James Clerk Maxwell formalized his ideas mathematically, giving us the Maxwell-Faraday equation. But here's the trick. EMI looks like just a set of equations, yet physically we can observe two distinct phenomena. Motional EMF, where a conductor moves through a magnetic field, and transformer EMF, where a stationary conductor is exposed to a changing magnetic field. Now, why divide EMI into two groups? Because when you look at applications, the distinction makes perfectly sense. Let's start with motional EMF because this is where we actually see electricity in motion. The first application that must have come to your minds is the electric generator, a mechanical force causing rotation that produces current. It's a great example of the Lorentz force in action. The simple motion of spinning a coil in a magnetic field is what produces our entire energy infrastructures. But motional EMF goes beyond generators. Take the SC maglev train for instance. By using strong magnetic fields to make vehicles float above a guideway, magnetic levitation eliminates mechanical friction and enables much higher speeds. This system relies on EMI for both propulsion and levitation. Superconducting magnets are used in the train's electrodynamic suspension system. According to Faraday's law, an EMF is induced in conducting cores embedded in the guideway as the train's magnets move past them. By Lenz's law, the resulting eddy currents create magnetic fields opposing the train's motion. This interaction generates the repulsive force that lifts the train. Impressive, right? Motion, speed, and energy. That's the beauty of the motional EMF.
I see your point, but I'd argue that the real elegance of EMI lies in its static form, the transformer EMF. It all starts with its name, the transformer, a static device operating on a changing field. It's a direct demonstration of Maxwell's Faraday equation in its integral form. The line integral of E dot dl around a closed loop equals minus the time rate of the change of the magnetic flux through the surface. No motion here, just a changing flux yet. It's the foundation of our entire power distribution system. Another device we use without much thought is the curing clamp. It uses a split core transformer to measure AC current without electrical contact or cutting the wire. It works purely because an AC current produces a time-varying magnetic field, which rates the time rate of change of the magnetic flux. The clamp detects the effect of the changing flux, no generator-style motion, just field dynamics. We also mentioned wireless charging. Two static coils, one in the charger, one in the phone, and the field generated by the base coil induces current in the phone's coil. There are countless other applications that make you wonder how much a simple coil and a magnetic field can revolutionize our world. But before you go, tell us what fascinates you more about the electromagnetic induction. The motion that generates current, or the static field that does it without moving at all?